Good afternoon, everyone. My name is Greg Risterman from Olympus NDT. I'd like to welcome everyone to this webinar on the benefits of phased array inspection for corrosion mapping. Our presenter today is Chris Magruder, who's a phased array AUT manager working out of our Quebec facility. This webinar is budgeted for about 60 minutes. The main presentation should last approximately 45 to 50 minutes, leaving 10 to 15 minutes for questions. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the course of the presentation. Do not type them into the chat panel. We will not monitor the chat panel for normal Q&A. If we don't get to your questions during the live event, they will be addressed personally either by email or by phone after the event is done. This presentation, along with the Q&A, will be archived on our website at www.olympus-ims.com by early next week. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, all yours.
Good afternoon, everybody. We're very happy to present this information to you from Quebec, Canada this afternoon. I saw a lot of attendees in the panel that I know and haven't seen in a long time. We are here today to talk about the benefits of phased array inspection for corrosion mapping. This all started with basic hard wedges underneath a linear probe attempting to collect either data points that would traditionally be collected from a conventional UT scope or high-speed raster scanning with a two-axis scanner collecting C-scan data. As that customer base has started using these in the field more, we developed two systems to enhance the inspection. The first one has been out for a couple years now, and it's being widely used throughout the world, called a HydroFORM mapper that we see here, based on a water column. And the new system that has just recently been released, that some of you already own, I saw on the panel list, is the RexoFORM system. The RexoFORM still uses a hard wedge, but it has a guide system that allows it to be placed with a flat wedge on a curved surface without rocking the probe and with some customized enhanced water coupling. Both these systems, like many other applications, are designed to easily integrate with the standard software in the OmniScan MX2 and its new latest generation OmniScan MX2. In traditional conventional corrosion mapping, we use a two-axis high-speed raster scanner. This requires a laptop in the field, extensive training in the software, and to run the scanner and program the scanner. They would use one or a series of dual-element conventional probes in a pitch-catch configuration typically, and a typical probe at 0.375 inches would have an effective beam of less than 200 thousandths, a very small individual data point. These raster scanners require enormous speed, a lot of heavy equipment, and again, the laptop in the field to acquire a C-scan data. And when we look at the conventional pitch-catch probe compared to the phased array probe like you see here, in a conventional probe, we will have individual lines at the scan resolution within the probe. One individual A scan per white dot, or what we call the scan resolution. In the phased array versions of those inspections, we use a very large footprint probe with many small elements. So we achieve the same beam quality, or better, with a much larger footprint. This allows us to use smaller, simpler mechanical scanners, typically pushed by hand, but still exceed the productivity of the XY conventional raster scanners. And the added benefit of the phased array is with the dense data point, we get improved resolution, better sizing, better detectability, and a better overall characterization of the data for determining the flaw failure mechanism. And 12 times more coverage in this example we see with the phased array probe. The electronic raster phased array probe uses a 4-element aperture. So most of the probes that we're using are 0.6 or 1 millimeter pitch. So the large 1 millimeter pitch footprint using 4 elements gives us the beam quality of approximately a 4 millimeter conventional probe. We step through the probe in apertures like you see here. So any one A scan is sharing several probes. We're essentially replacing the mechanical raster scan with an electrical scan in one of the axes. This simplifies the mechanics. It allows us to use push scanners and small encoders in one axis and still acquire high precision data points. And we can see here that the low density, typically 2, 4, or even sometimes 1 millimeter from a conventional raster scanner, compared to the point density that's possible with the phased array probe. One circle essentially equals one A scan, summed together in a C scan, B scan, and D scan presentations. So the two systems we want to talk about based on the MX2 instrument is first the HydroFORM. And again, this is the water-based version of this inspection, and the RexoFORM that we'll explain in a moment is the hard Rexolite wedge version. So the system consists of the OmniScan instrument, a minimum of a 1664, since the typical probes are 60 or 64 elements and are not used with a second or third probe. That instrument is sufficient for the overwhelming majority of these customers. Any of the existing 32 128, 16 128s, of course, are compatible as well. Standard software. The Olympus HydroFORM mapper is the buggy you see here that comes with magnetic or plastic wheels, water column that we'll see in the next slide. The Olympus 2-axis chain scanner is adaptable for different diameters by changing out the links. It's encoded in this axis and in the scan arm. It uses a standard 7.5 megahertz probe. It uses consumable foam seals for the water column that we'll see in the next slide, and this does require a fixed water supply. In the mapper that you see here, there's a small consumable foam seal with a Teflon coating that allows the water to be contained within the column. It allows this mapper to slide over rough surfaces and some minor external corrosion to contain the water column. It needs to be free of bubbles. It takes less than 5 minutes to change out the seal. Depending on the surface condition and the production rate and how much tension you have to put on the gasket, these seals can last a month or less than a shift and require changing. And again, it's a very short, quick change-out time for the seal. There's an adjustable water column that you see here. As the diameter of the pipe is changed, the probe can be articulated. One side fixed will keep the probe parallel to the pipe surface. And we'll also explain about a synchronization on echo feature that allows this to be very efficient for the data sizing. This can perform inspections on a convex surface from 4-inch ODs to flat, or an internal inspection on a concave surface from 10-inch IDs to flat. And since we're using a water column, there is no wedge required. And since there's no wedge required, the only variable in the calibration is the water velocity, and you'll hear more about that shortly. The combination of plastic and magnetic wheels can optimize this. If I'm using it in a buggy capacity like you see now, or using it with an integrated scanner. When using it in the buggy configuration you see now, it does have a built-in encoder right here. The HydroFORM system also uses the large 1 millimeter pitch version of the probe. So using the standard default aperture of 4 elements, that gives us approximately a 60 millimeter coverage, or what we would call a stroke. So the scanner's moving in one axis, the stroke is the electronic axis of the probe. Now probes are also available for this this configuration at 5 and 2 megahertz. The umbilical is customizable, but comes in a standard 7.5 meters. Our typical inspection in this would mean 1 millimeter resolution in the probe, stepping 1 millimeter at a time per A scan, and 1 millimeter for the scan axis, or the encoder. So we get a 1 millimeter by 1 millimeter C-scan. And using the default configuration with points and the range and thickness, scanning speeds of approximately 100 millimeters per second are normal. The max scan speed has more to do with the water and the surface condition of the part. We define the near surface resolution as the ability to detect the flaw within that distance of the outside surface. And for the water column, we get an optimized pipe to water interface, which minimizes that, and it's about a 1.5 to 2 millimeters depending on the surface condition. For those of you who are OmniScan users and know the wizards, this uses primarily the linear scan at 0 configuration as opposed to sector or linear scan. And of course, multiple groups can be used at the same time using the linear. So we can do angle beam and 0 degree through the same probe at the same time in 2 separate groups. And then a very similar inspection as far as the setup, the data analysis, it's all the same, but in this we use a Rexolite wedge. Now, when we were using hard Rexolite wedges just on the pipe surfaces, they either rock when they're flat or when they're contoured, require a larger footprint, specialized water delivery couplant, and we're not nearly as efficient. So by adjusting this turn knob, loosens these guides and allows the probe to sit flat and flush, a flat wedge on a curved surface. The wedge footprint has been reduced significantly so that our diameter range is covered with one wedge. And again, this can be put into a scanner, the same chain scanner. The OmniScan was designed to be very integrator friendly for any XY scanners. It can be configured with just the use of a patch cable into the encoder inputs. And then when it's in its standalone version here, there are small ports for installation of the small Olympus mini wheel encoder that you see here. But the same basic inspection. We're replacing the mechanical movement of the scanner with an electrical probe raster. And of course, the benefits of the phased array and data collection we'll see shortly. So the 2 specifications for these, and you'll find this in the brochure as well, the HydroFORM using the I4 probe, the RexoFORM using either the A12 or A14. So these are very common weld inspection programs, and if you already own those probes, they can be used and are compatible with the mechanics that you see here of what we call the RexoFORM. This I4 probe is typically an immersion tank, so most of the customers I looked in the attendees unlikely would have that unless they're using a HydroFORM already. The maximum one-line scan coverage, again, with the 1 millimeter pitch, we have essentially about a 60 millimeter stroke. As you increase the size of the aperture, the coverage will decrease. So on very thick components, you might need more than 4 elements. We'll reduce that somewhat. The A12 is a 0.6 millimeter pitch and has a smaller footprint. HydroFORM cup water For the couplant medium, the delay line medium, RexoFORM uses the Rexolite. The HydroFORM comes with two delay line adapters that allow us to adjust the height of the water column. This is necessary when you're inspecting components when the second interface echo is interfering in your area of interest in the data. So these were designed to put that second interface, just like an immersion tank, 0-degree inspection, way out in time at 125 millimeters, and for the RexoFORM version of that at 50 millimeters. Another way of looking at that is if I'm inspecting something less than 50 millimeters, I don't have to worry about the second interface echo interfering in my area of interest. Near surface resolution, this is the little noise you see at 0 on your A scan, and it's improved by the water column. The surface condition and how much gain you have to use is going to change this somewhat. OD inspection range we covered. ID inspection range is not applicable on the RexoFORM because we cannot do ID inspections with the flat wedge. The footprint is quite a bit larger on the HydroFORM mapper. Scan direction is circumferential, so that means it's designed to scan on a pipe in this axis, not in this axis. And the scanner compatibility, again, these can be configured with the standard chain scanners or any XY scanners. We've recently had a third-party scanner company integrate this with a high-speed automated scanner. If any of you are interested in greater productivity, contact us directly, but you should probably see some more information shortly on the future for the automated versions of the HydroFORM. So in its configuration that you see here, we have the index axis that's used, and I'll crank this lever to adjust the position, and the scan axis here, encoded in both directions. An umbilical that's fixed to the chain scanner, some user-friendly knobs to hold it in position as you make the adjustments, and we'll see 60-inch strokes where we can achieve approximately 4 or 5 before we have to pick up the chain scanner and reset it in the next position. Both of these systems benefit enormously by the use of a water supply. Couplant is not recommended. The repeatability for scanning in 2 directions with the couplant is very poor. The RexoFORM, as it's a flat wedge on a round surface, even using the water sprayer here and providing a constant couplant supply enables you to absolutely minimize the amount of missed data points. The HydroFORM benefits even more by an electrical water pump, and that water pump, whether it's an Olympus or some third party, should be as free of bubbles as possible. Some of these, that was never a concern for the weld inspection, but now keeping bubbles out of the system makes the inspection productivity much better and the data results. So before we continue that was a little bit about the hardware, about both systems, what separates them, water versus wedge. The actual setup for these is very similar. In fact, it's the same with one exception I'll point out about the synchronization feature of the HydroFORM. But what we're going to do, and what makes these applications somewhat of a entry-level phased array application, is our ability to use one default setup file, make some minor changes to it to apply it to different thicknesses and diameters. So once you have the default file, it's pretty easy to see where the configuration is at for those of you who've been through OmniScan training and make minor corrections. But in the most part, it's not really necessary. From materials as thin as a couple millimeters to even a 25, 30, 40 millimeter thick carbon steel, we would basically be using the same file and just adjusting the part thickness, some of the UT parameters like the range and the gate, and acquiring data with the same setup file. So The setup file for all of these, including the HydroFORM and different versions of the RexoFORM using different wedges, will be available in the installation on the default directory. So after loading that file, we will enter the part thickness for what we're going to inspect. We will adjust our UT parameters, including configuring the range. One of the probably the most common thing we see from customers when we're looking at data, mistakes they make, is improper range, meaning mostly it's way too long, and improper gate position and gate logic. And we'll talk a little more about those when we get to that. The point quantity of the A-scan is very important, and we will configure a TCG manually, not using the wizards. Then we will configure our displays, relevant readings, the thickness range for our statistics, the color palette of the C-scan, and then we will configure our scan parameters, name the file, and do the inspection. So it's a fairly short process compared to a typical phased array weld inspection from scratch and calibrations. So in the default OPS file, for version 3.0R3 or later, which includes some of the MXU customers out there as well, specific features for the corrosion mapping, including the C-scan compression, readings related to the corrosion mapping, modified color palette behavior, updated probe wedge database, including the new probes and RexoFORM wedges. All of those you'll find after that version, and of course for the MX2 users, it's best just to download the current version from the website as things get improved or fixed regularly. So if creating a file using the group setup wizard from scratch, you'll also find the appropriate wedges for either the HydroFORM or RexoFORM in the wedge database. So it makes it fairly simple as well. In our UT range in DB, we set the UT range to start before 0 a little, so the pipe interface signal is visible. And I noticed there's some people in the audience that don't own OmniScans or are considering buying them and might not know a lot about the phased array. So basically, this S-scan display that you see here is a way of visualizing many individual A-scans together. We're converting an A-scan to a color amplitude plot. So the blue line represents the individual A-scan. So I'm looking at A-scan number 12, or this A-scan is using elements 12 through 15. A-scan 1 would be using elements 1 through 4. A-scan last would be using elements 57 through 60, or depending on whatever probe you're using. So we're looking at this way, I can see all of the A-scans stacked together. So in this area we see here, this is the water-to-pipe interface, or the wedge-to-pipe interface. When using the HydroFORM, we need to ensure this is free of bubbles. So we start our range a little bit before 0. And at the pipe interface signal, we get our first signal, and then we have our first back wall, which represents the bottom of the part, and then the multiple back walls. So we want to set our range efficiently. If I have 320 or 640 points on my A-scan, by setting the range appropriately, I'm ensuring that the thickness readings are going to be as accurate as possible, and I'm not wasting data or creating a larger file or slowing down my PRF or anything like that. So this is typically what we would be looking at, and I can see 3 back walls here, back wall 1, 2, and 3, and we generally, again, we need to see at least 2. Then we set our gate position. For those of you who've recently upgraded your software for the MX2s, you're going to see some new options in the gates. Previously, we had the ability to use just the edge or the peaks. Now you'll see first edge, max peak, and several different other options. For the corrosion mapping applications, we don't care much about amplitude. So The gain is usually very high, signals over 100%, and we're going to take our measurements from the leading edge of the A scan. So in this example, the red gate A that you see here, I'm going to be taking the reading from the edge where it interfaces the gate, not from the peak data here. And that results in a much more accurate inspection, allows us to increase the amplitude without decreasing the accuracy of the thickness readings. So I want gate A monitoring the first back wall, and I want gate B monitoring the second back wall. We want gate A as close to the interface as we can without interfering, without touching it. So in analysis mode, it's natural for us to reposition the gates or move them around a little bit as we find corrosion, and as the thickness at different sections of the pipe, it's normal we might have to make an adjustment and do individual A-scan analysis for certain data points. In the OmniScan setup, you'll also find the point quantity. This is normally set to 320 by default, and for the weld inspection is not so critical because the use of A-scan compression allows us to retain amplitude while reducing the resolution in the time axis. So if our procedure is requiring a 0.1 millimeter thickness reading, I need to ensure that my range divided by the number of points is at least what the minimum thickness requirement for the procedure is. So it's normal for these applications that we would increase the number of points in the A-scan. That is directly related to file size as well. And depending on the thickness accuracy that you need, you can dramatically change, improve, or reduce your maximum file size by manipulating this. The file sizing capacity for the MX2 is 300 megabytes. I saw there were some MXU users in the attendees list, and unless you bought an optional larger hard drive at the time of purchase, most of those older OmniScans are limited to 160 megabytes. So the next thing we'll do is the TCG. Now, there's no code requirement for sensitivity calibration or time-corrected gain, but what using the TCG does, it allows us to increase the amplitude of the backwall signals without increasing the amplitude of the surface interface signal. When we talk about near surface resolution, and we'll see it a little better on some larger displays shortly, the larger this interface signal is, the more difficult it is for us to detect and measure a reading in that area. So I can move this gate very close to this as long as it's small. So using the TCG allows us to boost these signals without boosting this one. If I just increase the gain, the near surface resolution here becomes poorer, and this signal increases in size. We would create a 2 or 3 point TCG. I just type in manually. I'll have an add point option, enter in the position of the first back wall, and manually increase the gain until the signal is approximately 100%. Hit add point, type in manually the position of the second back wall here. You see the little red dot, and increase the gain until the second back wall is approximately 100%. And that will result in our best results. After the UT is configured and the A-scan is satisfactory, we will configure our displays. These are already configured in the default setup files if you use them. The A, S, and C scan display that you see here, we would typically use for the setup and analysis, but during the inspection, it's normal to just enlarge the C-scan display or even put the C-scan display full screen while we're acquiring the data. The gate thickness is something that the weld inspectors typically don't ever have a reason to use. So those of you who are new to corrosion mapping but maybe an expert on the OmniScan, it's a part of the program that might be new to you. But under the gate alarms menu, under thickness, we're going to configure how we want the A-scan to read the thickness reading. And as you see here, typical of a conventional flaw detector or an automated conventional system, all of the gate logic is available here. And then we enter in a thickness range. Typically 0 to the nominal thickness is where we would start. By entering the thickness range here, it sets our scale for the C-scan. In this case, on the scale, we see 8 to 10.5, so it was a modified. It will eliminate any reading statistics from outside our area. So once I've acquired the data between 0 to the nominal thickness, I will determine my lowest point in the C-scan and make an adjustment here so those invalid or non-relevant readings, no acquisition readings, 0, one of the gates bled into the other gate, I can eliminate those erroneous readings from my data by limiting it here. And again, that sets the purple scale that you see here beside the C-scan. And after we have this scale defined, we go to Display, Properties, and set the color palette for the C-scan. Normally, the default, and for most of the applications, we're used to seeing an amplitude-based C-scan, where color is representative of the amplitude. But in these applications, color is representative of the time of flight or position C-scan. So once we've defined the purple ruler for our minimum and maximum, now we can scale the color palette within that. And once we acquire the data, I'm going to slowly increase this value until I start to see some red in the C-scan. And that will show me where the low points are. And by adjusting the color palette between the minimum and maximum reading, I will ensure the maximum amount of contrast to look at the data. Again, the color palette. So before we do the inspection, on almost any UT procedure that we do, we're required to calibrate the system. Now, whether we're physically calibrating and making changes or verifying the calibration, we need some type of record of it. In the image you see here, we're using the HydroFORM system, which means there's a water column. So simply placing the step wedge on the seal or up against the RexoFORM hard wedge, we can take a reading all the way across the step wedge. And then we can either take a screenshot or a very small data sample like you see here. So here we can see the different steps of the step wedge. So once I take a small data sample, just placing the wedge against this, I can see that the wedge here, representing the 300 3/1000th of an inch step, is in this A-scan. And then as I move the A-scan over to here and to here or to here, I'll see and verify the other steps. And we would expect a fraction, again, a very, very tight specification, as good as the conventional thickness readings for sure, especially if we're using the water column with a synchro on echo mode. And again, we can include either a screenshot or a small data sample for the permanent record. Prior to the inspection, also, in addition to the calibration, probably the most common question we get asked is, what is the smallest defect this can find? what are the minimum separation between two small defects that this can differentiate. So it's not uncommon that the customers will build a performance demonstration using flat-bottomed holes. It determines both the ability to size them, the ability to detect small ones, the ability to detect near surface resolution, and it would be a series of holes at different depths and sizes that we would scan to determine if we're using the correct frequency, aperture, so on and so forth. If this is done on the same nominal thickness as the inspection, you can be sure your results are going to be repeatable. And in this case, we have a C-scan image of multiple strokes. As you see, the buggy isn't large enough to scan the entire plate. So even in this configuration, I can encode the scan, take one line, move the scanner, bring it back, and I can piece that together either by pausing the instrument, by repositioning the encoder. With a little practice and not using a two-axis scanner, you can achieve a very high precision C-scan with a little bit of a practice. Some cases, we'll use a combination of plastic and magnetic wheels depending on how we want to manipulate the small scanner. And again, here we'll see an offline analysis, which we'll do. We see the A scan, the side view, the end view, and top view all at one time. And a typical, we have many examples of this where a 1 millimeter flat-bottomed hole and 2 millimeter near-surface resolution is very practical. So our encoder setup now, either using the HydroFORM water version or the RexoFORM Rexolite, in the one-line scan configuration, we need to enable one encoder and determine that encoder as the scan axis. The OmniScan MX2 as a two-axis input. So the software will determine our maximum scan speed. We program one encoder, set the polarity and the resolution based on the steps, and preset this as needed to acquire the data. In the latest version of the MX2, which does have an improved acquisition speed and a larger file saving capacity, we calculated that you can drive the one element pitch probe in a 60 element configuration using the default file over 15,000 millimeters in the 300 megabyte file capacity. So whether you did multiple line scans or one continuous line, we have about a 15,000 millimeter scan based on the 300 megabyte file saving capacity. And when we're configuring this in a two-axis scanner, we will select the raster scan and program encoder 1 and encoder 2. We will tell the software which encoder we want to assign to the scan axis, which is typically encoder 1. So this is the mechanical axis, and this is the electrical axis where we will step the buggy over 60 millimeters at a time. And like I had said, now that customers are using this and acquiring a lot of experience, they are finding that they can map out 60 millimeter stroke on the pipe, acquire a circumference of data, move the mapper without this axis, but do it manually, reset the encoder position, and build a C-scan with a surprising amount of precision, even without the two axes. So now after we have, and just to review briefly, we loaded the default file, we configured our UT, we configured our display, we configured our gates and color palette and scan encoders. So now we set the length of the C-scan. In a one-line scan like you see here, this says 0 to 60, and I only see the scan. If this were a two-axis scan, I would have 0 to whatever I programmed, and I would have the other axis here. So I'm scanning from 0 to 550 millimeters here, and this is mechanical. Every 1 millimeter the scanner travels, the software is recording every A scan for every aperture in this axis. And now we'll see an acquisition movie. This movie is a pretty typical with the most common 2-axis chain scanner that we use. This movie can be downloaded from the website or viewed on the website as well. So for those of you that might be on a little slower internet connection, it might be a little bit choppy. You can come and see that on the website.
Grab the chain scanner with 2 hands and place it around the circumference of the pipe, keeping it as parallel as possible to the pipe surface. Reach around with 1 hand and grab the hook and set it and clasp it tight. We'll flood the water column we'll shake the scanner to ensure it's free of bubbles. We will use the C-scan layout for the inspection. Hit the Start Acquisition button that will reset the encoders, and we're ready to start acquiring data. Move the scanner slowly and smoothly. If you miss any lines of data or have a problem, you can back the scanner up. It's writing data in both directions. We complete the first stroke. Back to the start position. While watching the index axis encoder, I'm going to scoot the scanner over on the index axis to 60 millimeters with about a 1 millimeter overlap between strokes. And begin acquiring the next acquisition. Again, while watching the index axis, I'm going to move the scanner over another 60 millimeters. Ensure that we're not missing any data. We have enough overlap. Bring the scanner all the way around back to the 0 position. And the data file is ready to be saved.
So I hope most of you were able to see the movie. Again, go to the website if it was a little bit choppy or with the audio. We had some comments about that. I'm also receiving a lot of questions regarding the bubbles. Bubbles in the HydroFORM get in the way of the data. Having a water supply where all of the fixtures are tight and secure and it's not sucking air into the system dramatically improves this. Keeping the water supply immersed in the water and not allowing it to have bubbles inserted into it in the beginning also makes this much easier. And certainly the water supplies provided from Olympus take this into account. We see some of them out in the field from third parties where that was never a concern, and it's causing a lot of problems. So the next series of slides are some examples of the different types of defects and what they looked like. Here we see an example of leaching. General corrosion, we can see the fine or the river bottom of the component here. This is the surface interface. Here we see general corrosion. Another general corrosion we see here. This looks a little different because it was acquired without the video filter. Now available, just recently released, is the OmniPC offline analysis software for the OmniScan. So this is the same user interface as the MX2. It allows all of your previous data files from earlier generations of OmniScans or the latest MX2 to be analyzed offline. You basically have all of the functionality in the software that you would have on the instrument on a data file in pause mode. So to go over a couple of things that we talked about, when we set up our gate under the gate thickness menu, the nominal value of the pipe was 15 millimeters, so we acquired the data with a very small or very large range, almost a range of the entire thickness for the gate. This range that we enter in here will limit my readings here so that I don't see erroneous data. I'll come back and adjust this once I've really found the minimum spots and recorded the data. I can also reposition the gate if necessary. So under my display, properties, color palette, we're going to use the color palette to help us perform the analysis on the C-scan. And again, this represents the electronic scan for each focal law across the probe. This represents the mechanical movement of the scanner, and we have a data point in this case at every 1 millimeter. The data can be taken at a minimum. It'd be the steps revolution of your encoder. But typically, most of the procedures we see require a millimeter on thicknesses up to about 25 millimeters, and then it would be at 2 millimeters, on something larger than that. So we go to the color palette, and I'm just going to slowly raise this 1 millimeter at a time, watching the color palette. So I can see low spots coming in here and here. And this color palette will determine where the red starts to appear in the data. So as I slowly limit the range of this, now I've found the low section, and we will measure that in another way shortly. But I want to find where the minimum red shows up, right here, making sure that some of this is still uncorroded at the nominal thickness, like we see this data point here. So between 4.8, 4 millimeters to 15, I've got the low spots here. This indication is a 1 millimeter diameter flat-bottomed hole at 6 millimeters deep. We would not expect that type of quality and resolution from a typical 5 megahertz 3/4 or 0.375 inch dual element conventional probe. So it's very good. And as I just scroll through the data here, I can see the detail on the bottom of the corrosion. I could use a cursor to map out sections. So I would put it right at what we call the river bottom of the corrosion as I move through the data. Now, our readings here, in the OmniScan, you have 2 lists of 4 readings each that will appear on the report and at the data file. Since we're saving the full A scan, those can be changed at any time. If you use one of the default files, in those readings are already pre-configured lists of useful readings typically used with corrosion. So using these readings, we also have a series of readings that have a Z in them, and that means zone. So if I create a zone with my cursors, and on the offline analysis version of this, there are some tools built in, keyboard shortcut functions, keystroke shortcuts that allow us to overcome not having the touch screen on our computer, but using the same software as the instrument. So I'm going to create a box with the reference and measure cursors, this red cursor here and this green cursor. Within this box we call the zone. So the lowest reading that occurred in the zone was 5.72. That number cannot be smaller than the thickness that I determined here. And once I find the minimum thickness, I can eliminate zeros or false erroneous readings from my statistics by making the adjustment here under the gate minimum. And I could also change this logic. Why would we ever use a B minus A gate configuration for the reading? For instance, if the pipe or vessel had a paint coating and we needed to eliminate that paint coating by using back wall to back wall, which is similar to what the conventional instruments call echo to echo, we can do that. So the lowest reading in the zone was a 5.72 millimeters, and it occurred at 63 millimeters on this axis and 25 on this axis. And it amounted to a metal loss of 15.7% based on the part thickness of 15 millimeters. So we also have the full screen option as well. Similar to the instrument, I have all of the same displays, and we normally use our A, S, and C reading here, and I can generate indications and print reports exactly with the same functionality as the OmniScan instrument. And again, you haven't seen this yet. It's just coming out this week, but on the website you'll see some product information and some new product introduction literature and brochures for this as well. But it's an extremely useful tool now that we don't need to have the instrument for the offline analysis. Another example of corrosion. In this case, we see some general corrosion here. We see the bottom of the component, the surface interface. Another example, multiple back walls here, losing in time. Again, have to do a scan analysis to verify the validity of individual data points or suspect areas from the C-scan. External corrosion for the HydroFORM mapper, where the corrosion isn't so severe, we can see the external corrosion as well as the internal. And when we use the TomoView offline analysis, another software program, in the TomoView we can see here the HydroFORM, the data was collected unsynchronized. So when we look at every individual stroke, we can see the 60 millimeter strokes here. One side of the probe may have been slightly higher or lower than the other side. So we can create a synchronization gate. We can resynchronize the data. And that's essentially the same as lateral wave straightening. In the offline analysis now, we can create a customized C-scan and perform analysis with a similar set of tools for zones and the minimum thickness. I can see the B-scan and D-scan simultaneously. And it has an output function so that we can export the data file, either the A-scan or C-scan, to a third-party external analysis program similar to Technical Toolbox or one of the other commercially available systems. Isolated pitting. Although this is a corrosion mapping WebEx, we also use the HydroFORM RexoFORM for fabrication as well, for near-surface defects. It's a very similar inspection. And using the TomoView data report here, we would see a sample of the file export functionality for text comma-separated text values or text values in a raw TXT file. So that concludes the technical part of this presentation. I'd like to thank all of you for joining. I'm going to turn this over to Greg in Waltham to wrap things up for us. Again, we had a lot of questions. We will answer all of those by email, and you'll have a contact to come back with us should you need anything else that you didn't get from those answers. Take it away, Greg.
Thanks, Chris. Great job. We are getting to the 1 hour mark here almost, so on behalf of Olympus, I'd like to thank Chris for his participation in today's event. And thanks very much to all the attendees that joined us this afternoon. We hope the material presented was informative and useful. The webinar, along with the Q&A questions from both sessions today, will be archived on our website at www.olympus-ims.com by early next week. Please feel free to check back often, and there's a lot of information on the website if you haven't been there. And also, to reiterate, if you need to see that video again, the video is up there. It'll play better over the web probably than it did here. And that's going to do it for today. Again, thank you, Chris. Great job. And thanks to everyone for participating, and we'll see you again next time.